So welcome everyone. Today we have the pleasure to have Dr. Tatsuo Kawai in our sixth lecture. About the videos being available, we are finalizing their processing and they will be uploading the official MGH YouTube channel, but I will email everybody as soon as we get the videos there. So last week we had 83 participants, so it was great. So thanks for everybody that watch us and keep coming every week, please. About the questions, if you have questions, you can submit it by 3 different ways. You can use the chat tab, the Q&A chat tab, or you can hit raise your hand button that we can connect you to the speaker later after the talk. If you experience any technical problems, please communicate with me via chat directly. You can select my name and send me a message. And at the end, we're gonna send you an email with a survey. So please give us your feedback. It's very important to us to keep improving the webinars and the talks. And also we give the feedback to the speakers as well, which is, I think it's important to them too. So now I'm gonna turn to Leo that he'll introduce Dr. Kawai.
Thank you, Thiago. It is my pleasure to introduce Dr. Tatsuo Kawai, who is a professor of surgery at Harvard Medical School and the surgical director of the Living Donor Transplant Program and the Dialysis Access Program at MGH. He's also the A. Benedict Cosme Chair in Transplant Surgery. He's doing like an extra effort today because he was doing transplants all night last night, and he's here joining us despite his tiredness, and we really appreciate that. He is a leader in clinical transplant tolerance in the world and has led many of the efforts in kind of moving this from the animals to humans, and it is really our pleasure to have a webinar today entitled Clinical Tolerance, an update, and I'll turn it to Dr. Kawai to begin today's webinar. Thank you again.
Thank you, Leo. Hello, hope you can hear me well. If you cannot, please raise your hand to let me know. And also, welcome to stop my talk anytime if you have some question. It's better than talking to the computer alone for 1 hour, so kind of weird without seeing audience. The title of my talk is Clinical Tolerance 2020, an update. But since this lecture is supposed to be for trainees, I would also cover the background of each tolerance strategies. So for this audience, I believe I don't need to explain why tolerance is important. Achieving tolerance in clinical transplantation has been our holy grail, and it appears more important during pandemic as mortality rates of transplant recipients by COVID-19 have been as high as 35%. We are seeing a lot of death of the transplantations. So what is the definition of tolerance? I got this slide from Dr. David Sachs. According to David, tolerance can be defined as the specific absence of destructive immune response to a transplanted tissue. So, but the tolerance may not be rock stable, as even tolerance to self-antigen can be broken, as you can see in various autoimmune diseases. I stole this slide from Dr. Ben Cosme, and this is Ben's favorite slide. There are countless strategies to induce allograft tolerance in mice. However, so far, only 2 strategies, Treg transplant and chimerism induction, have been successfully translated to monkeys and humans. Treg transfer is very recently shown effective to induce tolerance in clinical liver transplantation, but so far unsuccessful in clinical kidney transplantation, which is less tolerogenic than liver. Chimerism induction is the only strategy that is reproducibly successful to induce tolerance in clinical kidney transplantation. So what is chimera? The word chimera is originally derived from this monstrous creature in Greek mythology that has a lion body with a head of goat protruding from its back, tail is snake. It's kind of very so scary image. But therefore, I'm talking about chimera, so I looked for something adorable. So this is also kind of a chimera. Old folks may not know, but it's a mix of Pokemon and Mickey Mouse. Anyway, the term chimera has come to describe anything composed of very disparate parts and was thought highly implausible. However, chimerism actually existed very close to us. That is a free mating cow. The cattle usually have singleton pregnancy and twins are rare. And free mating cow is a female calf born as a twin with male brothers. Over 90% of the such female calves are infertile. So it's a very serious problem for dairy farmers because I cannot see the difference of the free mating just looking back from the outside. So if if they buy this kind of a free mating cow, they don't produce milk. So it's going to be a lot of financial loss. Therefore, the description of free mating can be seen since 16th century. But no one knew why this free mating is infertile. But finally, in 1917, Frank Lilly discovered the reason. He discovered a connection between the two fetal circulatory system through the placenta, like this. There's a vascular osmosis. So androgen of the male fetus circulate into the circulation of the female fetus, then interfere the development of reproductive organs. So about 35 years after Lilly's discovery, Ray Owen in Wisconsin found erythrocyte chimerism in free mating. Since this erythrocyte chimerism can be found in adults, he speculated that it is not simply interchange of erythrocytes, just erythrocytes moving to the other brothers or sisters. Erythrocyte, the lifespan of erythrocytes is only 120 days or so. So if it continues, the chimerism continues, he thought that progenitor cells must be mixed during their embryonic period. His insight was right, and they actually have a chimerism in all lineages of hematologic cells. And you can see mixture of cells with XY from the bladder and XX from the free matching the own cells, chromosomes. Around the same time, Peter Medowa in England found that most free matching twins accept the skin grafts each other, so the skin can be exchangeable. This was published in Heredity in 1951. And in free mating, cross-circulation through the placenta resulted in persistent mixed chimerism and skin allograft tolerance. So Medowa hypothesized that tolerance may be inducible if the recipient is exposed to the allogenic antigen early in fetal life, and performed a seminal experiment called neonatal tolerance. In his experiment, he infused allogenic cells. Actually, hematopoietic cells is only effective, but allogenic cell infusion is done to the fetus or neonate. And then mixed chimerism is induced. Then those animals accept allo skin graft from the allogenic cell infusion donor. Indeed, his hypothesis is right. And mice successfully accepted skin from the donor of the infused cells. And this is the first study of that successfully induced tolerance, and he was awarded 1960 Nobel Prize. Do you know this gentleman standing next to Medova? This is our Dr. Rasa. So he studied at the Medova's lab and brought transplant immunology to MGH. So we're kind of connected to Medova via Dr. Rasa. This figure is a little bit busy, but bear with me. It shows chronological achievements on tolerance via chimerism. White is immune study, and green, blue is non-human primate studies, and yellow is clinical studies. Since Owen discovered persistent mixed chimerism in free-matted cattle, three strategies, transient mixed chimerism, persistent mixed chimerism, full donor chimerism, has been pursued to induce allograft tolerance. I categorized Medova's neonatal tolerance as transient mixed chimerism, as most studies determined that chimerism is induced in neonate was not persistent. Therefore, the mechanism of tolerance may be different from free-matted. In 1964, Barner reported the possibility of inducing allograft tolerance by a transient chimerism. However, his finding remained unheeded until we found the transient chimerism is inducible of the renal allograft tolerance in non-human primates. Allograft by a persistent mixed chimerism has been achieved in various murine models. However, persistent mixed chimerism has been extremely difficult to achieve in primates and has only been achieved in HLA-matched transplant recipients by the Stanford group. Mixed chimerism study by David Sachs was translated to non-human primates, but we found the transient chimerism is sufficient to induce renal allograft tolerance in non-human primates. This has been successfully translated to both HLA-matched and HLA-mismatched human kidney transplantation. Finally, full donor chimerism was until recently considered too risky because of GVHD. However, full donor chimerism and renal allograft tolerance have recently been achieved by the Northwestern group in HLA mismatched kidney transplant recipients. In 1980s, David and his group successfully developed a clinical applicable regimen to induce mixed chimerism in mice. His non-myeloablative regimen consisted of monoclonal antibody against CD4 and CD8, followed by low-dose TBI, 3 gray. 3 gray is acceptable. Even we give a 3 gray to the animal, they can recover even without bone marrow transplant. And thermic radiation. He found thermic radiation is essential. Then after bone marrow transplant, those animals developed persistent mixed chimerism and accepted skin allograft tolerance. When I came to MGH as a research fellow under Ben Cosme in 1991, I was assigned to translate this David's mouse study to non-human primates. After struggling for 6 months, we were fortunate to find out this regimen can induce mixed chimerism. The original regimen includes TBI, TI, ATG, and we needed splenectomy in addition to combined kidney bone marrow transplant. Then followed by 1 month course of CNI. Later, we successfully replaced splenectomy with anti-congenital blockade. So this is the chimerism observed in the first successful monkey. When we started to see chimerism increasing, it was very exciting as this was the first successful mixed chimerism induced by non-myeloablative regimen in monkeys. However, it declined over time and completely became undetectable by 1 month. At this point, we predicted that his kidney will be rejected once cyclosporine is discontinued. However, it didn't. This monkey did not reject kidney for the subsequent 14 years and died due to old age. We also transplanted skin graft 1 year after kidney transplant, but the skin was accepted in donor-specific fashion. What we found from those experiments in non-human primates was transient chimerism was sufficient to induce tolerance, at least for the kidney allograft. When we consider clinical application, there was some concern to use TBI as part of conditioning. Fortunately, by that time, Dr. Spitzer, Tom Spitzer at MGH Hematology successfully developed cyclophosphamide-based conditioning regimen for HLA, identical combined kidney and bone marrow transplantation for myeloma patients who developed kidney failure. The regimen includes cyclophosphamide instead of TBI, followed by TI, and ATG, and CKBMT, and followed by cyclosporine for 2 months. So very close to the monkey protocol, except for cyclophosphamide. Based on monkey results and the protocol for myeloma, this regimen was developed for regular renal failure patients without malignancies. Expecting more effective T-cell depletion with less risk of GVHD, ATG was replaced with anti-CD2 monoclonal antibody. Because of humoral response observed in a couple of patients, we added pre-transplant rituximab in the modified regimen. The first patient enrolled into our tolerance clinical trial was 22 years old patient who rejected her first kidney. She got the first kidney at age 12 from her father, but this transplant was complicated by warts that was caused by human papilloma virus infection. Because of this, she was not able to walk. It's very difficult to walk and could not do any vigorous outside activities. She eventually lost her kidney function due to rejection and became the first patient of our study. After transplant, she did well and completely discontinued her immunosuppression by 10 months. And her warts all disappeared after discontinuation of the drugs, and she became able to do vigorous outside activities. And 18 years after transplant, her kidney function is still pristine. This is a summary of MGH clinical trial with the first initial trial. And 7 out of 10 achieved primary endpoint, which was 24 months graft survival in the absence of maintenance immunosuppression. No infectious complications and no patient death was observed. And we have 3 kind of modification and depends on the rituximab. So NKD03, we didn't include any rituximab. And modified NKD03, 2 doses of rituximab was added. And ITN036, we have 4 rituximab. All patients developed chimerism, but very brief. They disappeared by day 14, most of this. But they survived long term, all survived over 10 years. Longest one is getting close to 18 years, and 11 years is most ongoing survival. But 3 patients lost kidney graft at 12.5 years and 10.5 years and 10 years. This patient lost due to recurrent MPGN, and these 2 patients lost their kidney graft due to chronic rejection. A duration of the no immunosuppression ranging from 10.3 years, 4 years to up to 17 years. So those initial results is very encouraging, but we encountered serious adverse events. That is acute kidney injury, potentially cytokine release due to cytokine release. If you look at acute kidney injury by looking at this figure, this is serum creatinine days after transplant. After day 10, the creatinine started to go up. Most of the patients, except for one patient. The first patient didn't have any acute kidney injury, but most patients develop this kind of acute kidney injury. The highest creatinine can be close to 16, but they all, most of the cases, recover to the normal by day 30. By just giving steroids, but some patients required treatment with some globulin or plasma exchange because it was difficult to discriminate the response from the humoral response. This acute kidney injury was associated with recovery of lymphocytes, especially T cells, and was associated with loss of chimerism. Sorry. The biopsy shows mainly interstitial hemorrhage and endothelial injury, but no rejection. We occasionally see some cellular infiltration, but some small level of CD8 positive cell infiltration. But it has not been observed in HLA identical CKBMT. Therefore, this response may be arrow response against the HLA. Since this response, acute kidney injury, was not observed in monkeys, and we tried to replace the cyclophosphamide with a TBI and tested in 2 patients. And first patient developed chimerism and successfully discontinued immunosuppression, but second patient failed to develop chimerism. Then anti-CD2 monoclonal antibody became unavailable, and we replaced anti-CD2 monoclonal antibody with host ATG and belatacept. And this protocol is exactly same as monkey protocol, which was successfully induced tolerance in monkeys. However, monkeys and humans are a bit different. Monkeys are a bit more resistant to develop chimerism with a TBI, and both of them didn't develop great chimerism, and therefore immunosuppression was not discontinued. And the last patient also developed ATM. Fortunately, our collaborator, Samsung Medical Center in Seoul, Korea, found the solution. We have been collaborating with them closely since 2010, and they also encountered AKI with the initial protocol, but successfully made a minor modification of our protocol. They added a low-dose fludarabine, 10 milligrams square meter at 4 doses, but instead, cyclophosphamide dose was reduced to 22.5 milligrams from the 60 milligrams per kilogram. So let me talk about tolerance by persistent mixed chimerism, in which Stanford tried to achieve. So at Stanford, Sam Strober has been studying induction persistent mixed chimerism using total lymphoid irradiation, TLI. In this report in 1977, mice are irradiated with TLI and received MHC mismatched bone marrow cells. So TLI dose is 3,400 watts, which is a very high dose. But this is only treated, and then followed by bone marrow transplant, and skin allograft is done after establishing chimerism. With half much of the combination, most of the animal accepted skin, with a full mismatch. About half of the animals accepted skin. And if you irradiate bone marrow, it doesn't work because they need a chimerism to induce this tolerance. So based on these research on TRI, some Stroban Jones Scandling at Stanford group developed this protocol. So following kidney transplant, 10 doses of TRI is given, then ATG and cyclosporine MMA. And donor mixture of the donor CD34 positive cells, hematopoietic stem cells, and CD3 cells given to the patient 1 day after completion of TRI. And then cyclosporine MMA is slowly tapered off. This is the Stanford results. In HLA match transplant, 29 patients is enrolled, and 28 patients developed chimerism, and 24 patients stopped immunosuppression successfully, and 10 patients still have a stable mixed chimerism, and 14 is only have a transient chimerism, but stable tolerance. One patient didn't develop chimerism, and the immunosuppression was not stopped. In a HLA mismatch transplant patient, however, 27 patients enrolled, but only 6 patients developed stable chimerism and attempted to stop immunosuppression. However, 2 of them developed rejection and back on immunosuppression, and their chimerism became lost after stopping immunosuppression. So the chimerism was immunosuppression dependent chimerism, and 4 patients was back on immunosuppression.
Tatsuo, can I ask a question?
Yes, sure.
In the HLA match group, is that a partial matching? Because they still didn't have full chimerism, and they did have some chimerism, so some of the HLA antigen.
I think this is matched. So I think at least, HL 6 antigen match.
Okay.
ABDR.
So what is the meaning of chimerism? What is the marker that distinguishes the donor from the recipient?
They are using PCR, tandem repeat.
Oh, okay.
So it's not seen in HLA.
I see. Okay, thank you.
Okay, so overall, they are successfully induced HLA matched kidney transplant, but not been successful in HLA mismatched transplant so far. Based on this initial results of Stanford, Dixon Kaufman at Wisconsin organized a multi-center trial called the MEDAL trial, in which 33 centers are involved to induce tolerance in HLA matched kidney transplants. So far, 11 patients have been enrolled, and 3 patients successfully stopped immunosuppression for the period of 2 to 6 months. The protocol is completely the same as the Stanford protocol. So next one is tolerance induction by persistent donor chimerism. That has been attempted by Northwestern group. This is nothing different from the regular bone marrow transplant, and entire host hematopoietic cells are replaced with the donor cells to induce tolerance. Obviously, GVHD is the most concerning with this approach. To overcome GVHD, post-transplant cyclophosphamide protocol is an important innovation. The idea was originally developed by Eisenberg in the 1960s. He identified the best timing of cyclophosphamide given after transplant, which was day 4, day 3. Then this idea was extended by Kikuo Nomoto at the Kyushu University in Japan. And in their protocol, BMC infusion is administered on day 0, then followed by no immunosuppression for 3 days. Then large dose of cyclophosphamide is given on day 3. During these 3 days of no immunosuppression, the donor alloreactive T cells and host alloreactive T cells both are fully activated and proliferate. Then large dose of cyclophosphamide is given on day 3, then to kill those cyclophosphamide, kill them all. Then they say bidirectional deletion of alloreactive T cell clonal deletion destructions are happening. So by doing this, by prevent the GVHD, also inducing tolerance. Then those animals accept the organ or skin transplant done 14 days after transplant. This strategy was then successfully translated to clinical BMT by Luznik and Fuchs at Johns Hopkins. This was a major breakthrough in BMT, as the incidence of GVHD has been significantly lowered in HLA haplo-identical BMT. So their protocol consisted of ATG, cyclophosphamide, fludarabine, TBI. So the important thing is no immunosuppression for 3 days, then followed by large dose of cyclophosphamide. Another innovation is identification of facilitating cells. If you get rid of those T cells from bone marrow cells, the risk of GVHD will be reduced. However, it will also increase the failure of stem cell engraftment. T cell itself also facilitates the engraftment of stem cells. But Ildestad discovered mixed cell population that facilitate the engraftment of hematopoietic stem cells as well as prevent GVHD. Facilitating cells express CD8 but no TCR expression. And has several mechanistic studies done to prove B-reg induction by these cells and T-reg induction. And this FC cells also prevents apoptosis of HSC, prevents apoptosis of HSC, and prevents GVHD. Based on these innovations, Leventhal and Ildestad at Northwestern developed a protocol to induce full chimerism without GVHD. So protocol is close to the Johns Hopkins protocol, includes fludarabine, TBI, cyclophosphamide, but followed by large dose of cyclophosphamide 3 days after kidney transplant. And also, they added FC, facilitating cells with hematopoietic stem cells. Then cell-septum tacrolimus is slowly tapered off by 1 year. This is a representative patient date of the chimerism. So after 5 months, the chimerism is completely 100%. This is Northwestern results. 37 patients enrolled, and 27 developed durable chimerism, and 26 achieved tolerance. So it's like 70% of the enrolled patients, which is, I think it's really good. But they have 2 graft losses and 3 deaths. 1 death is due to GVHD, and 1 from lung cancer, 1 pneumococcal sepsis. And those 2 graft losses somehow related to infection. So full donor chimerism is supposed to be considered to be immuno-incompetent state. So that's why they may encounter those infections or cancers. So we need to see the longer term results of this approach. 8 patients only developed transient chimerism, and with their protocol, transient chimerism cannot induce tolerance, and therefore immunosuppression was not removed. And 2 patients failed to develop chimerism. Okay, finally, want to move to tolerance by Treg infusion. If you culture recipient T cells with irradiated donor lymphocytes and a cosmetic blockade for 2 weeks, suppressor T cells such as Tregs are known to be induced. The idea is to infuse these suppressor cells into recipients to induce tolerance. So let me explain this. The first demonstration of kidney tolerance by Treg infusion in NHP, non-human primates, was reported by a Japanese group in 2005 in JCI. Ko Okumura is a dinosaur. He's famous for suppressor T cells in 1970s, but still, he must be over 80 years old, but still very active for any kind of immunologic studies. And he collaborated with surgeons and did these studies. And his protocol consisted of first splenectomy and kidney transplant on day 0, followed by just 2 weeks of cyclosporine and 3 doses of cyclophosphamide. Then they culture irradiated donor cells and recipient cells for 3 to 7 days under cosmetic blockade with anti-CD8 and CD86. Then those analgesic cells, they initially said analgesic cells, never said Treg infusion, but Treg enriched analgesic cell infused to recipient on day 13. Then with a full protocol, about half of the monkeys achieved long-term survival, but without those cells, they all failed. With a third-party stimulation in MLR, it didn't work. That means analgesic cells needs to be donor-specific. Then without cyclophosphamide, it didn't work. And either anti-CD86 alone or anti-CD80 alone in culture didn't work. So dual blockade is necessary. So this approach was extended to clinical kidney transplantation by Teraoka, Satoshi Teraoka and his group at Tokyo Women's Medical University. Actually, Satoshi Teraoka is my Japanese mentor. And Dr. Teraoka is, the first group is treated with exactly the same regimen. The group is exactly the same regimen with monkey. And group B in splenectomy was replaced with rituximab. This idea has probably came from the experience in ABO incompatible kidney transplant, because initially we needed to do ABO incompatible kidney transplant with a splenectomy. However, that was successfully replaced with rituximab. So that's probably ideas from the experience in ABO incompatible transplant. Then in group C, just rituximab and ATG and cell infusion was performed. However, none achieved immunosuppression withdrawal in all groups. Some patients achieved monotherapy of the tacrolimus, but some patients developed DSA instead. Now Okumura Ko is very tenacious, and now worked with Todo. Todo is used to be a professor of Pittsburgh and right-hand man of Dr. Tatsuo, and they did a very difficult procedure using Okumura's protocol. So first, this is the living donor liver transplant. So first, they did a leukapheresis from the donor and get lymphocytes. and irradiated. Then also did a leukapheresis from the recipient, then culture mixed together under the blockade of CD80 and CD86 for 2 weeks. Living donor liver transplant is performed with a splenectomy. They are very exactly following the monkey results. Then on day 13, those cultured cells are infused. The results is good, great. They have tested in 10 patients, and 7 of them achieved tolerance, and often suppression for over 3 years to close to 5 years. And their survival, graft survival is from 5 years to 6.6 years. Liver function is great. And 3 patients who failed to achieve tolerance is all the liver failure from autoimmune hepatitis. So some autoimmunity, increased autoimmunity prevent the induction of tolerance. This is published in Pathology in 2016. So encouraged by the total studies, Jim Markman developed a protocol with ITN. Different from total studies, the recipients had deceased donor liver transplant and pure Tregs have been infused. Antigen-specific Tregs have been generated by Winan at Dana-Farber. The protocol is this. First, we do a liver transplant, as usual. At the time of the liver transplant, donor cells are saved. And after 2 to 4 months, leukapheresis is performed to obtain recipient lymphocytes and then do a mixed culture with the donor cells, irradiated donor cells, under beratacin. Then create generate alloantigen specific Tregs, and then infuse back to the recipient. Before Treg infusion, cyclophosphamide is given. Then tacrolimus and rapamycin slowly together. 21 patients enrolled, and 12 actually got the transplant, and 7 met study continuation parameters. Then, but the 2 terminated early, but 1 completed TAC withdrawal. He's still on RAPA, but he recently got biopsy, and if his biopsy is okay, RAPA will be stopped. And remaining 4 is on both tacrolimus and RAPA. And if your biopsy is good, and first tacrolimus is stopped, then rapamycin. In conclusion, initial clinical studies have shown that tolerance in clinical transplantation is possible. Efficacy and safety need to be improved. Study for clinical tolerance needs long-term observation, typically over 10 years to conclude the efficacy of the study. So this is acknowledgements, and we're kind of getting too old. We need some energetic and ambitious young people who can take over what we have done so far. So looking forward to work with you in future. Thank you very much for your attention. Thank you very much. Bye-bye.